Wow.
All right, hello everybody. Okay, some announcements. Another reminder that your next Achieve is due on Monday. This is the second part of Chapter 8 and the first part of Chapter 9, which we will get through today. Next week, I have regular Monday office hour at 1. It's okay. Wednesday office hour is going to be at 2, and then I'll have another Thursday office hour at 1:30. And then, of course, we have our recitation next Wednesday at 8. So if you need any extra help or review before our final, those are good times outside of class to do that. And we are going to go ahead and get started with Chapter 9. So Chapter 9 is about periodic trends. So we'll be looking at the periodic table and talking about trends that we can use the periodic table to understand and see the patterns. And we'll talk about ionic bonding. All right. Ready to go. So this is a pretty short chapter. We'll get through more than half of it today and then finish it on Monday and begin Chapter 10. So our first section is about valence electrons, which we've talked about a little bit already. So I mentioned them in Chapter 8. Valence electrons are the electrons that occupy the outermost shell. So this is the highest energy, highest principal quantum number. So we'll say this is the highest occupied shell. So electrons that are in the shell with the highest principal quantum number n. And if you have any partially filled d shells or partially filled f shells, those are also valence electrons. So these are the electrons that are involved in bonding. So they're the most accessible, they're the outermost electrons. They're the most accessible by other atoms. And so these are really what we're concerned about when we're talking about bonding reactivity. And atoms that have the same valence electron configurations tend to have similar chemical properties. So we'll talk about that as we move along. But first, let's do this learning check. So first, write the noble gas electron configuration for lithium, and then identify the number of valence electrons, and then do the same thing for bromine. So I'll give you all a minute or so to start working on this, and then we'll go through it together. Yeah. All right, if we are writing the noble gas electron configuration for lithium, we look to the periodic table. Lithium's in the second row. So if we go one row up all the way to the right, that noble gas is helium. So we put helium in brackets. And then lithium is in the first column and in the second row. So it has one electron in its 2s shell. Any electron after helium is a valence electron. So lithium has one valence electron. If we do the same thing for bromine, bromine is in the fourth row. So noble gas before bromine is argon. Argon's at the end of the third row. So then if we continue with the electron configuration, we have 4s2, 3d10, and 4p5. So bromine is the fifth element in the p block. How many valence electrons does bromine have? It's not 5. It's not 10. It's 7. Yeah, it's 7. So the D shell is filled, so we don't worry about the 3D. We're worried about orbitals that have, or we're looking at, we're not worried about anything, but we're looking at orbitals that have the highest principal quantum number. So that's the S and the P orbitals. We have 5 in the 4P, 2 in the 4S, so it's a total of 7 valence electrons for bromine. Bromine and the other halogens, so in the same column, all have 7 valence electrons. So we can look at different groups, and elements that are in the same group have the same valence electrons. So for example, in everything in the first row would have, or first group, first column, would have a half-filled S shell as their valence electrons, as a valence electron. And so everything in that first column has one valence electron. So that's sodium and lithium. They're both in this column. They both have one valence electron. And all elements in column 2 have 2 valence electrons. All elements in column 13 have 3. This is also column 3A. 2 different ways to label columns. 14 or column 4A has 4, and so on. Column 18 or 8A has 8 electrons, except for helium. So because all of these groups, the atoms in these groups have similar valence electrons or have the same valence electrons, they all have similar chemical properties. One that we've talked about so far is a charge. So elements in that first column tend to have a +1 charge. Again, that's to lose 1 electron and then have a filled valence shell from the previous quantum number. So we can determine the number of valence electrons in an atom by the group number. So groups 1 through 8, so if we go back one slide, we have groups 1 and 2, and then all the way to 8 over here have valence electrons that are the same as their group number. So potassium, group 1, 1 valence electron. Tungsten, W, group 6, 6 valence electrons. It has 2 6s electrons and 4 5d electrons. So adding those together, we have 6. For groups 12 to 18, so now we're looking at this group 12, and to the right, their number of valence electrons is their group number minus 10. So nitrogen is in group 15, but you subtract 10, it has 5 valence electrons. For groups 9 to 11, so a couple of groups in between, those valence electrons are not always consistent. They can't be stated unambiguously because the electrons may or may not participate in bonding. This is beyond the scope of our course. So we won't be worried about determining valence electrons for those atoms. But most of the atoms that we talk about in our course are in the S block or the P block. And so to find the number of valence electrons for those atoms, we can look at that labeling with the A letter here And that's the number of valence electrons. So 7A, 7 electrons, 6A, 6 valence electrons. And again, that's true for all of the atoms in the same column. So, for example, oxygen in group 6A, 6 valence electrons. Carbon is in group 4A, 4 valence electrons. And then you can always write out the electron configuration and determine number of valence electrons that way. And that's it for this section. And we'll move on to atomic sizes. So as we increase in principal quantum number, so that is the row number, if you're going down the periodic table in a column, so increasing in principal quantum number, those orbitals become larger. So the 5s orbital is much larger than the 1s orbital. So we increase in principal quantum number, we increase in orbital size. Also, you might remember when we drew the orbital energy diagrams, when we drew those orbitals on an energy scale, so energy increasing bottom to top, the 1s orbital is the lowest energy, and then 2s, and then 2p, et cetera, et cetera. So as atomic orbitals become larger, they also become less stable. And so this is the trend when principal quantum number increases. This is going down a column which is also referred to as a group. So that's our trend going down, up and down the periodic table. Lower on the periodic table, we have larger atoms, or larger atoms. If we're going across a row, so left to right, those atomic orbitals become smaller. Smaller atomic orbitals means they're closer to the center of the atom, center of the nucleus. Electrons being closer to that positively charged nucleus is a stabilizing effect. So smaller and more stable. This occurs as atomic number, or Z. Capital Z is our symbol for atomic number. As that increases while n is fixed, so that means you're working in the same row, but you're increasing in principal quantum number, orbitals become smaller. So this is across a row or a period. Let's look at periodic table and kind of understand why that is. So as we go, let's start with left to right. As we're going from left to right in a single row, so electrons are occupying orbitals with the same principal quantum number, orbitals are shrinking. As we're going left to right, number of protons in the nucleus is increasing. So you have electrons, so if this is our nucleus, electrons are in the same energy level as you go across a row, but you're increasing in number of protons in the nucleus so they can pull the electrons a little bit closer to the nucleus. So that's why the atomic size decreases when you're increasing number of protons, but you have your electrons in the same shell. So that's going across a period. As you're going down a column, you're adding electrons to larger and larger orbitals, so the atom is getting larger and larger. So our largest atoms are this bottom left corner of the periodic table. Our smallest atoms are in the top right corner. So here are larger atoms and smaller atoms up here. We're talking about stability as well. So if orbitals are shrinking going left to right, that means electrons are getting closer to the nucleus. So the stability of the atom overall, because overall the electrons are closer to the nucleus, that increases. If we're increasing in principal quantum number, we're adding electrons are further away from the nucleus, then they're at higher energy levels, and so overall stability is decreased. So larger atoms are less stable, smaller atoms are more stable. Talk a little bit more about nuclear charge. And we're going to compare helium with a +1 charge. So helium with a +1 charge has 1 electron. And then hydrogen, neutral hydrogen, also has 1 electron. So we have the same number of electrons in these two atoms, but the difference between the two is the structure of their nuclei. Hydrogen is the first element on the periodic table, has atomic number 1, it has 1 proton in its nucleus. So a single proton, so +1 charge in its nucleus. Helium is element number 2, atomic number 2, so it has 2 protons in its nucleus and 2 neutrons. Neutrons don't contribute to charge at all, so its nuclear charge is +2. So both of these atoms, helium with a +1 charge, because it lost an electron, and hydrogen, neutral hydrogen, they have 1 electron, but helium has 2 protons. That means that the electron in helium with the +1 charge is held closer to the nucleus. So helium is a smaller atom. The higher nuclear charge attracts the electrons more strongly. So having a +2 nuclear charge for helium attracts that outer electron more strongly than the +1 charge for hydrogen. We'll talk about difference in cation and neutral charges, or atomic sizes in a little bit. But this periodic table here, Dem, do you have a question? Yeah.
So the helium is going to be closer to the nucleus than hydrogen?
Yeah. Yes, because there's 2 protons in the nucleus of helium, and protons are positive, electrons are negative. So the electrons are attracted to the protons. So you have more protons in the nucleus, the electron is closer. Okay, so this periodic table here shows the difference in atomic radii sizes for different atoms. And let's define this here. So atomic radius is the distance between the nucleus, so the center of the atom, and the outermost electron. So small atoms, small atomic radii. So we can see our largest atoms are down here, bottom left side of the periodic table. They have electrons in highest energy shells and fewest number of protons for the row. As we go left to right in this bottom row, electrons are still in the same energy shell, but we have more protons in the nucleus. So the distance between the nucleus and the outermost electron is lower as you're going across the row, because those protons can pull in the electrons. And then going down a column, we're adding electrons to a higher energy level, so they're further away from the nucleus. That's why we have a larger atomic radius. Atomic radius is measured in picometers. And so we have actual values here. You can see the difference between, for example, oxygen and fluorine is 6 picometers, 4 picometers. So fluorine is the atomic radius is 4 picometers smaller because fluorine has 1 additional proton in its nucleus. The next graph here shows trends for atomic radii across different periods. So lithium sodium, potassium across that top arc up there. Those are elements in the first column. And then right here, for example, all of these dots represent different atoms in the same row as lithium. So you start with lithium, that's the largest atom in its row, and then it decreases as you go across the row. Neon is the smallest. And then we can see the same trend across, although there are some different trends when we're within the D block and F block, which we won't concern ourselves with for this semester. But the overall trend, that left of the periodic table is smaller than the right, and lower on the periodic table is larger than the left, or than the top. Okay, let's do this iClicker now. So you have two questions. Which of the following pairs are larger? And then why? So the two questions, you're just, on iClicker, you're just picking one. One is larger than the other, or they're the same. But as you're working on it, discuss with the people around you why one is larger than the other. And not just that it's left of the other element or to the right of the other element or above or below. Think about the location of electrons, principal quantum number, size of orbitals, number of protons, things like that.
No, correct. It has more shells. But like in the same way, things to the right. Yeah. Yeah, this is left.
Okay, maybe 20 more seconds. Looks like most are done. All right, closing here. Okay, which is larger, silicon or chlorine? Why silicon? Less protons. Yeah, less protons. So silicon is to the left of chlorine in the same row. So they're both in the third row. They have electrons in the third energy shell. But silicon is to the left, so that means silicon has fewer protons. It's 14 protons. Chlorine has 17. So chlorine with a larger number of protons in the nucleus holds those electrons in the third energy level a little closer to the smaller atom. And then how about sulfur versus selenium? Selenium, and why is that? N is larger, it's lower on the periodic table. So that means that the electrons in the outermost shell of selenium are in a larger orbital. They're further away from the nucleus. So yes, selenium has more protons, but that does not outweigh that the electrons are in a larger energy shell. So higher principal quantum number outweighs the effect of having more protons. So that's why we can only compare number of protons if we're in the same row, so same principal quantum number. Questions on atomic sizes, any of these trends? Okay, so we've talked mostly about sizes of neutral atoms. This is all about the distance between nucleus and the outermost electron. If we're taking away electrons, so we're creating a cation, then the atomic size will change. The ionic size will be different. Or if we're adding electrons, the ionic size is different. So a cation, if you think about number of electrons in a neutral atom surrounding a nucleus, they all feel some pull to the nucleus. They also repel each other, and that causes the electrons to spread out a little bit. By they repel each other, I mean the multiple electrons that are in the same shell. So electrons have a negative charge, they'll repel each other. If you remove an electron, so to create a cation, now we have fewer electrons in that outermost shell. There's less electron repulsion, and they can feel a stronger pull to the nucleus. So a cation is always smaller than the same atom with a neutral charge. If you're taking away an electron, the remaining electrons get closer to the nucleus. Then if we think about a neutral atom, so nucleus, electrons, we add another electron to the outermost shell, or even a higher principal quantum number, then those electrons repel each other. So the electrons spread out more, and that causes the ionic size to be larger. So an atomic anion, negative charge, is always larger than the neutral atom. In both these cases, we have the same number of protons if we're taking away an electron or adding an electron, but that electron-electron repulsion is the key factor here. And so this next slide shows relative sizes of neutral atoms and their common ions. So over here we have column 1, lithium, sodium, potassium, rubidium. As a neutral atom, they have some atomic size, and the atomic radius in picometers is shown on the left. But most of these atoms exist as a +1 cation. And so if they're losing an electron, then their ionic radius decreases. We can see the difference here by almost 60 picometers between neutral atom and positively charged atom here. And the difference is, it depends on the atom, but in general, if you have a neutral atom, again, that's larger than the cation. Over here, we have atoms on the right side of the periodic table, so column 7 and column 6. Column 6 typically exists as a with a -2 charge, like oxygen up there. And so if these atoms gain electrons, then their atomic size increases. So neutral atom is on the left, ion is on the right. We have a larger ion because we've added electrons. All of the halogens exist in nature with a -1 charge. So with that extra electron to get that -1 charge, we're increasing the atomic radius. All right, let's do another learning check here. So we have 3 statements here. You are selecting which of these are correct. So calcium neutral versus cation, fluorine neutral versus anion, and then carbon and lithium both are neutral. So on iClicker, you can select more than one answer. That's not a hint that you need to, but if you find one that's true, don't discount the others. So think about all 3 of these, determine which of these are correct. And let me know if you have questions. Yeah. Yeah, so they, intelligence is to a charge. There was this the minus one charge. And so the radius with that charge is larger than the neutral is. And the six. Okay, now everybody, you can only select one. So there's a clue that only one of them is correct. But think about all three of them. And we'll spend one more minute on it. Say 30 seconds. All right, I'm gonna end it here. Okay, so calcium neutral larger than calcium cation. Is that correct? It is correct, yes. So calcium cation, we've lost an electron. Cations are always smaller than the neutral atom. So this one is correct. How about fluorine neutral larger than fluorine anion? Incorrect. Fluorine with an anion with a negative charge that had gained another electron, same number of protons in the nucleus. So an extra electron with the same number of protons means that atom is a little bit larger. The anion is a little bit larger. And then how about carbon and lithium? Carbon larger than lithium? No. Let's go back to this slide here. Lithium and carbon are in the same row. You can see the difference, 75 picometers versus 130. So lithium is a lot larger because it has fewer protons in the nucleus. Carbon has more, so it holds the electrons closer. So let's talk about isoelectronic species and the difference in sizes here. So isoelectronic species, we define these on Wednesday. These have the equal numbers of electrons. So same number of electrons, but they are different elements, so their properties change with their number of protons, so Z. the elements that are in this table here, O with a -2 charge, fluorine with a -1 charge, neon, sodium with a +1, and magnesium with a 2+ charge, all of these have the same electron configuration. They have a noble gas configuration, 1s2, 2s2, 2p6. So all of these have 10 electrons. So same number of electrons, but we have different elements, so they have different numbers of protons. The way the table's organized is by greater number of protons, so C. Oxygen has fewest of the protons in this row. You look at its atomic radius at 140. We increase in one more proton and we decrease in the atomic radius. So one more proton is holding these 10 electrons closer, so we have a smaller atomic radius there. These radii were determined by ionic crystals, and we can't measure neutral atoms with ionic crystals. So we don't have an ionic or a radius here, but we can imagine it somewhere between 133 and 102. And we're decreasing as we increase in, so we're decreasing in the radius size as we increase in number of protons. So stronger electrical force between the nucleus and the electron cloud results in a decreased ionic radius. This last row, we haven't talked about what these mean. So EA is electron affinity, ionization energy is IE. We're talking about those in the next section. But I wanted to include this row here still, because it'll make sense after we talk about those. But let's just write a note, have not discussed this yet. Yes.
So what is a nuclear charge?
The nuclear charge, so the nuclear charge is the number of protons.
Okay.
And then in the next slide, we'll talk about effective nuclear charge. And that's the charge that can be felt by different electrons, because all electrons are attracted by the same number of protons. We'll talk about that on the next slide. But nuclear charge, number of protons. Other questions? Okay, let's continue on. So this section, we'll first talk about ionization energy. This is energy required to remove an electron. Before we talk about ionization energy, we need to talk about a few other properties, including nuclear charge. And we'll use this example of helium to kind of understand this. So we're in the mind, our reference point is that we're thinking about helium with a +1 charge. So helium has two protons in its nucleus. It has a +1 charge, that means it has one electron orbiting the nucleus. So the nuclear charge is +2. That attracts, we're saying we have a free electron up there, not bound to any other atom. That, with a negative charge, that electron is attracted to the nucleus with a +2 charge. So an electron can now, if it gets close enough, will orbit this +2 charge nucleus. But what's actually, the charge that's felt by that outer electron is not a full +2, because we still have one electron that's already orbiting this atom that is causing some repulsion between the two electrons. So we have electron repulsion. That electron repels, the one that's already orbiting, repels the other electron that might come in and bond. When they're both already orbiting the nucleus, or they're both orbiting the nucleus, the electrons cause what we call shielding, or cancellation screening is another way to think about it or label it. This is the result, or this is a way to describe, a word to describe that when the electron nears the atom, nears the nucleus, that delocalized charge, that one other electron that's present here, isn't completely offsetting the +2 neutral charge. And so the resulting charge that we have here, we call this the effective nuclear charge. The nuclear charge that can be felt by that second electron is not a full +2. It's less than +2. It's still greater than +1, but it's less than +2 because of this other electron causing some repulsion to that second electron. The shielding effect and effective nuclear charge will help us understand trends in ionization energy. So we'll talk a little bit more about shielding. This depends on the size of the orbital. So electrons in smaller orbitals that are packed around the nucleus, they cause more shielding. They're tighter to the nucleus, they're closer to the nucleus, cause more shielding to the outer electrons. The effectiveness in screening, I'll use both terms. The effectiveness of shielding, so the degree to which an electron shields other electrons, decreases as that electron's orbital size increases. So if we think about an atom, let's go back to our nucleus, we have electrons in multiple energy levels. An electron close to the nucleus is shielding the outer electrons from the nucleus. So that has a stronger shielding effect than an electron that's all the way out here. It would shield any additional electrons that are further away, but not to the same degree because it's all the way out here. It is also shielded by all the electrons closer to the nucleus. So the effect of shielding of an individual atom is lower for an electron that's in a higher energy level, higher N, than an electron that's in a lower N, closer to the nucleus. We have this diagram here. We have our positively charged nucleus in the center there. The 1s electrons so this is representing spherical s orbitals. 1s electrons closest to the nucleus, they shield 2s electrons, they shield 3s electrons from the nucleus. If there were 4s electrons or 4p electrons, they would shield all of those outer electrons. The 2s electrons shield the 3s electrons from the nucleus, but the 2s electrons don't shield the 1s. You have to be closer to the nucleus to shield. Electrons close to the nucleus shield electrons only that are further away. So n equals 2 electrons provide effective screening or shielding for the n equals 3, n equals 4 in larger orbitals, but little to no screening for the n equals 1 orbital. Okay, so electrons that are further away from the nucleus feel less of an effective charge from the nucleus because electrons that are between the outermost electron and the nucleus are shielding that positive charge, blocking that positive charge from being felt by the outermost electrons. Okay, we'll keep that in mind when we talk about ionization energy in the next couple of slides. Ionization energy is the amount of energy required to remove an electron completely from an atom. So again, here we're comparing hydrogen and positively charged helium. Each of these have one proton and just one of these has one proton. Hydrogen has one proton and 1 electron. Helium has 2 protons. With a +1 charge, it also has 1 electron. Okay, so if we take neutral hydrogen and remove an electron, so now we have H plus and a free electron, that requires 2.18 times 10 to the negative 18 joules of energy to remove that electron. Helium with a +1 charge, we've got 1 electron that can be removed, but now we have 2 protons in the nucleus. To remove that electron, 8.72 times 10 to the negative 18 joules are required. So 4 times the amount of energy is required to remove an electron from helium with 2 protons than to remove the electron from hydrogen with 1 proton. So higher number of protons generally means that more energy is required to remove an electron. This also indicates that the orbital energy of the helium's 1s shell is lower, so it is a more stable orbital because more energy is required to then remove an electron than the hydrogen. So orbital stability increases with Z, which is atomic number, which is number of protons. Let's look at these trends for ionization energy. So first, ionization energy. Or IE with a subscript 1, is the energy associated with the loss of 1 electron from a neutral gas atom. So we have a neutral atom. We measure this when they are in gaseous form. We remove 1 electron to make it a positive cation, positive 1 charge. That's our first ionization energy. We could remove additional electrons and have a +2 charge, +3 charge. But if we're just talking about the first ionization energy, we can follow this general trend here. Left to right, first ionization energy increases. Think about what we know when we go left to right. We have atoms with electrons in the same energy shell, but we're increasing the number of protons. That also means the atomic radius is decreased. So outermost electrons are closer to the nucleus. They are held more tightly to the nucleus. They feel a stronger pull to the nucleus, so it requires more energy to remove one. So we can say left to right, the effective nuclear charge is also increasing. So first ionization energy increases from left to right across each row. All about number of protons there and energy levels of the outermost electron. We're going top to bottom. As we go down the periodic table in a column, electrons are occupying orbitals that are further and further away from the nucleus. When we're talking about ionization energy, we're removing an outermost electron. Those outer electrons, for one, aren't feeling as strong of a pull to the nucleus because they're further away. They're in a higher energy orbital. And all the electrons in between your outermost electron and the nucleus are shielding that outermost electron from that nuclear charge. So less energy is required to remove an electron from a larger orbital. So first ionization energy increases if you're starting at the bottom and going to the top of the periodic table. So increases from bottom to top. Atomic radius is decreasing as you're going from bottom to top. And effective nuclear charge is increasing as you're going from bottom to top as well. So highest first ionization energy is top right. and lowest would be bottom left. Now this is a general trend this is IE1. We'll talk about exceptions when we come back on Monday. So there are some exceptions, and that's on the next slide. Yes. Till Friday. Yeah. All right. Thanks, everybody. Have a good weekend. Don't forget about Achieve. And I'll see you Monday.
Two of them.